Hello everyone. We will be discussing the tutorial and the experimental demonstration of differential scanning calorimetry in this video. Differential scanning calorimetry or DSC is a category of thermal analysis of sample which basically used to measure the temperature induced changes and explains the physical and chemical property of the material. DSC measures the difference in the amount of heat that is required to increase the temperature of a sample and reference as a function of time. Here, both the sample and reference are kept at the same temperature. We will demonstrate this in our experimental work. The reference sample should have a well defined heat capacity throughout the range of temperature where scanning is taking place. DSA depicts the graph in form of endothermic and exothermic transition. Whether less or more heat flow to the sample depend upon whether the process is endothermic or exothermic. For example, in case of melting a solid into liquid, more amount of heat flowing is required to increase its temperature at the same rate to that of reference. This is due to the endothermic phase transition of sample from solid to liquid. Similarly, less heat is required to raise the sample temperature when sample will undergo a exothermic process. Clearly, a large number of studies have been using differential scanning calorimetry to measure a large number of sample properties. Now, these includes the study of crystallization, the glass transition temperature, oxidation, and many other chemical reactions. The mentioned changes involve change in the energy and heat capacity, which is detected by differential scanning calorimetry with great sensitivity. Broadly, the DSC is classified into two groups, the heat flux DSC and the power compensation DSC. So, in the heat flux DSC, sample and reference crucible are placed on a sample holder integrated with a temperature sensor. This is a very compact and lightweight system having low heat capacitance. However, in the power compensation DSC, both the crucibles are placed in thermally insulated furnace and not simply next to each other. The electric power that is required to maintain the state is required instead of the temperature difference as in the case of heat flux DSC. The typical heat flux DSC somehow looks like this. So, DSC consists of a measuring cell which contains a furnace and an integrated sensor that have designated slot for sample and reference. The sensor part of of the cell is connected to thermocouple. Now, these thermocouple have a role of recording the temperature as well as the temperature difference, which is basically to calculate the heat flux. If you see, this section is also having a heater which takes care of the sample when heating is performed. Here we have displayed the typical differential scanning calorimetry plot. The DSC results into a plot of heat flow as a function of temperature. This includes both the heating and the cooling profile. So if you look in the graph, the heating profile is labeled in blue and the cooling profile is labeled in red. They include both heating and cooling profile of the sample as per the required experiment. As per different convention, exothermic reaction in a sample depicts the positive or negative peak. The possibility, so if you look at the graph, All we can calculate from this graph is the onset of peaking, a peak temperature, which is also called as a transition temperature, the peak area, which will be a result of transition enthalpy, and then the offset or the end of that peak. Similar things we can do in the cooling profile. We can set the onset of cooling, the peak, and the end, including the area, which will tell about the transition enthalpy. The possibility of determining the transition temperature and enthalpy makes DSC a crucial study for studying various phase diagrams for chemical systems. Under certain conditions, area under the peak, this area is associated proportionally with heat evolved in the reaction. So now we will move to the demonstration part of differential scanning calorimetry for our better understanding.
Hello everyone, this is the demonstration video of DSC. The instrument is placed right in front is the DSC instrument from NetSec. It is a high performance analytical instrument and is very widely used for the analysis of thermal properties of the sample. The instrument has a capacity to function in the temperature range from -60 to 600, and let's now look at the instrument part of this particular DSC. So the instrument has a power switch which is placed at the back of the instrument, and the same is being represented in the front. So the power is on right now, and that's why there's a green button visible here. Looking at the furnace of the instrument, which we have actually discussed in our tutorial video. So now let's look how it looks like from inside. So this is the lid for the furnace, and then if you'll see clearly, then there are two fixed locations, and this is for these two slots are for the reference. One is for the reference and the other one is for the sample. So these are the fixed slots where we load the sample. Now let's try to look how the sample loading is done over here. The DSC analysis is very well taken care with the software which it is connected with. For the sample loading, now the sample loading takes place in a crucible. So if you look clearly, there is the crucible is made up of an aluminium pan. We'll show you how this aluminium pan looks like. So this particular is the lid of the pan, the DSC lid of the pan, and then there's a crucible which is again the same aluminium, and we load the sample in these aluminium crucible and cover it with a lid so that the sample doesn't get inside the furnace, or it doesn't spill inside the furnace. These are made up of aluminium, and similar to the instrument, the temperature range again here is from -60 to 600 degrees Celsius. So let's have a closer look of how this pan and the lid looks like. So this is the crucible. Okay, and the crucible is used where after the sample is being loaded in the crucible, it is covered with a lid. Now this lid, we will show you how we load the sample and how we cover it with the lid, and followed by there occurs a piercing inside, so that if a particular sample is volatile, then there can occur any kind of release which is taking place. So now let's look at the sample. The sample which we are loading, since our sample of interest is a salt solution, and therefore initially we'll load a control sample which is water. And let's now look how the sample is being loaded in the crucible. So we'll take a very small amount of the sample and we'll load it in the crucible. The advantage of DSC is that it requires a very low volume or the very low amount of the sample of your interest. So once a proper amount of sample is being loaded, this will be covered through a lid. The sample will be, after loading, we'll take the weight of the sample. So the weight which is being represented is is 0.071 gram. So this includes the sample weight as well as the weight of the crucible. So the already known weight of crucible is 23 mg, and we will subtract the weight of the crucible, and so now we know that the sample volume which we have is 48 mg. We will now bring the crucible back and we'll cover it with the lid. The handling of the crucible and the crucible and the lid is very sensitive, and it should be done using a sharp forceps. We will now pierce the lid. As I said, it will create a passage for the release. So yes, so this is how the piercing of the lid will take place. And now we will take the lid which is already being pierced, and we'll cover our sample in the crucible. This particular system, the crucible and the lid system, will now go to the hand press. Now we will place the system on the hand press. This will help for a proper packing of the sample so that it doesn't spill inside the furnace when we place it. Now it will be hand pressed for proper sealing. Once the sealing is done, we'll bring back our crucible to the desired location, and if you look, the properly packed crucible looks like this. We will now take the sample crucible out. This is the previously loaded sample crucible, and we will now place the freshly made crucible which is having our new sample, and we will place it in the sample slot. So there's one thing that I would like to mention here is these crucibles are one time use. So you can just use them one for a sample and you have to discard it later on. Now this one in the right is our sample, and on the left is the crucible for which is a blank crucible. It doesn't have any solvent or the sample inside them. When you load this sample inside when you load those crucible, it is always advisable to place them right in the center, and even if it is not, we just move it with a forceps or something to place it right in the center for proper measurements. So once the sample is placed, we will now cover the furnace system with the lids which are provided by the manufacturers. And final, there is the third lid. Before starting the analysis, we use nitrogen. Now this nitrogen is a parched gas which is used in the system, and it is used to create the inert environment inside the furnace. The nitrogen here is supplied in a controlled manner. So now let's look at how the analysis starts and how does it looks like in the software. Okay, there's one more thing, that is the systems comes with an intercooler. Now this is very beneficial when we go to the lower temperature. For example, as I said, the temperature ranges from -60 to 600. So for the lower temperature like -60, -20, this particular intercooler is helpful for creating the coolness in the system. Once the sample is properly loaded in the instrument, we will now try to operate
the system from the software which is provided by the DSC manufacturer. And this is the Proteus software where we do all the analysis. So we'll just open the file of DSC. So this is a platform where we'll do all the settings of the system calibration and running. We'll click on the file option and we'll click the new option to set up the new measurement. And this is the first panel where you can see the crucible which is placed. As I we have placed the aluminium pure slit, it shows that. Further, it has also shown the details of the furnace, the sample carrier, and then there is an information about the TC calibration, which is done already. Let's now move to forward and then we'll click the header option. Here we'll provide all the sample details, like we will give a specific name to the sample, which is, for example, we can put any name which we want our file to be saved at. We'll put here as sample S1 or S1. Now it is important that we have already taken the weight of our sample and we'll put the mass which was uh, which was measured, which is 48 mg here. If you see down there, there are few calibration steps, and we will need to load the temperature calibration file. It is already there in our system, so we'll just load the temperature calibration file. And similarly, there is one more thing. We will do that for we will do the same for the sensitivity calibration. We'll load the sensitivity calibration file. If you look, as I have already said, that the purge environment was maintained by nitrogen. So the details about the nitrogen rate and everything is also being specified in the software. So once this header program is done, we will now we will set the temperature program. If you look at the right side of this window, then it has information of step category, which involves initial standby, initial dynamic, isothermal, final, and final standby. So we'll start by starting a fixed start temperature, which we'll set as -20 degree, and then we will make a stage of isothermal. Now this isothermal stage is important because it will help in the attainment and maintenance of our initial temperature. So we'll set a isothermal time of around 2 minutes. That 2 minutes is sufficient for our experiment to get that stabilized -20 degree, which we want for our work. Further, we can put to the dynamic temperature range. So the dynamic temperature involves the end temperature which we will set for the experiment. So we require an end temperature of 120 degree Celsius, and we want a heating rate of 10 Kelvin per minute. Now these parameters are different for different experiments, and you need to optimize the sample according to, or you need to take these readings according to the sample which you have finalized. So finally we'll do a final temperature. Now this final temperature is not the end temperature. So since all the parameters has been set here, we can look that there's a initial temperature, the isothermal state, the dynamic programming, and then the final temperature. So all the parameters you can check and you can verify them before starting with the experiment. So once this is done, we can start the process. And once you click the start, if you see there are two temperature visual, if you see the temperature, the current temperature, it is 24.6 degrees Celsius. And if you see right here, this is the temperature which is currently available. And the current difference between the set temperature and the known temperature is 44, and the threshold here is 5. So once the difference reaches the threshold, the measurement will start and you will start seeing the graph. So currently the difference is a lot and it will decrease with time. So once the cutoff is reached, the experiment will start automatically. So now the current difference has reached to 6.5 Kelvin, and which is very close to the threshold. And soon, as it will reach to the 5, we'll start seeing the DSC plot. So now you can see that the plot has been started, where it will, if you see at the bottom, it will function as an isothermal at minus 20 degrees Celsius, and as we have given the time for isothermal of 2 minutes, you can see the same thing over here, and it is somehow reaching to the temperature which was the initial temperature which was being set by us. So now you see down there it says heating to 120 degrees Celsius. So now the current difference has reached to 6.5 Kelvin, and which is very close to the threshold. And soon, as it will reach to the 5, we'll start seeing the DSC plot. So now you can see that the plot has been started, where it will, if you see at the bottom, it will function as an isothermal at minus 20 degrees Celsius, and as we have given the time for isothermal of 2 minutes, you can see the same thing over here, and it is somehow reaching to the temperature which was the initial temperature which was being set by us. So now you see down there it says heating to 120 degrees Celsius. So now our heating cycle has initiated, and we will try to observe how the curve moves. So if you see now it has rise from minus 20 to minus 24. Sorry, minus 23. You can see the temperature is changing over there, and we are moving towards the heating cycle. Finally, the plot which we have gone for our heating, we got at two peaks, one major peak and there's one minor peak. So the major peak and the minor peaks are always calculated through their onset values, through the peak, through the onset value, through the peak, and through the offset value, where basically the peak ends. Apart from that, we also calculate the surface area under these peaks. So these are the information that we get from the DSC curves, and rest of the things we have discussed in the tutorial already. Thank you.